Hi, I'm Sougata Sen, and I'll talk about our work on using multitask learning approach for estimating missing emotion self-reports. This work has been carried out by researchers at AppCare and BITS Pilani Goa campus, India, researchers from IIT Kharagpur, India, and from Microsoft USA. To start off, let us consider a simple scenario that we often encounter while conducting user studies. Imagine a researcher plans a long term study where they plan to collect emotion self reports. The researcher starts the study, but somewhere during the study, a few participants drop off from the study. Indeed, this is a scenario many of us would have encountered and will be able to relate to. What do we do in such kind of scenarios? The most common approach is that we drop the participants' data in such cases while doing our final analysis. This discarded data, however, has an associated cost. The research team prepared the study and thus had time, effort, and resources that they had put into this study, which incurs certain costs, right? Thus, it becomes an obvious question if we can develop efficient approaches to help reduce these losses without having to rerun the user study again. Running the user study again has time and effort associated with it, which researchers want to avoid. Adding additional sensors might help in the process. However, adding new sensors has cost associated with it in a different way. And some of these sensors often raise privacy concerns. To address these questions, we have developed a multitask learning framework, MUSE, that aims to determine user similarity and estimate missing emotion self-reports of dropout users based on other similar users. Via MUSE, we were able to quantify user self-reported behaviors. We were also able to model emotion self-reports, thus allowing estimating missing self-reports. To validate MUSE, we conducted two studies. However, before delving into the user study details, let me describe the apparatus used to validate MUSE. To validate MUSE, we implemented an Android-based application for collecting the emotion self-reports. The self-report screen is shown here. Users could select either one of the four emotions out here: happy, sad, happy, stressed, relaxed. If they did not want to answer, they could choose the no response button as well. An obvious question out here is, how did we come up with these choices for four emotions? Well, this choice is based on the circumplex model of emotion. Emotions in this model are divided into four quadrants based on the level of valence and arousal. An emotion could reside in any one of the four quadrants. We, for our evaluation, selected one emotion from each of these quadrants. Let us describe the user study next that we performed. We performed a user study with 24 participants, of which 20 were males and 4 were females. All participants were students at an Indian university. Due to this homogeneity, we call this dataset as the homogeneous dataset. We installed our application on the participants' smartphones. The app would trigger a pop-up at various times of the day, and users could select their momentary emotion at that instance. Overall, we collected data for 6 weeks from these participants and obtained 5,677 emotion self-reports. We next wanted to quantify these emotion self-report behaviors of participants in the study. We quantify emotion self-report behavior of users with the help of, firstly, the emotion state transition. This is the emotion transition indicating the probability of the next emotion from the current emotion. Secondly, the emotion persistence time. This indicates the continued existence of an emotion. And thirdly, the emotion sequence length, which is the length of time of recurrence of an emotion before it changes. For emotion state transition, we represent it via an emotion transition matrix as shown here. Each element in this matrix represents the probability of transitioning from one emotion to another. Specifically, we calculate the probability as the ratio of total number of transitions from emotion X to emotion Y divided by the total number of transitions from emotion X to any other emotion. For emotion persistence time, we considered one emotion and identify all blocks of time where this emotion is reported. We compute the average elapsed time for each of these blocks. To compute the persistence time of that emotion, we compute the average of the average elapsed time. Let us consider this example that we are showing out here. Let us assume that happy emotion is shown by the blue text that is shown out here, and the other text, the black text, represents some other emotions. Okay, so from here we can see that happy emotion is represented in two blocks. In the first block, the emotion lasts for 2 hours and 3 hours. And in the second block, it lasts for 6 hours, 4 hours, and 2 hours. The average of the first block, thus, is 2.5 hours. And the average of the second block is 4 hours. Therefore, the overall emotion persistence time in this case is the average of 2.5 hours and 4 hours, which is 3 hours, 3 hours and 15 minutes, or 3.25 hours. To compute the emotion sequence length, what we have done is we identify the number of times a user has reported the same emotion at a stretch. In this example, for happy, the user reports happy for continuously for two instances out here and 3 instances out here, right? Thus, the emotion sequence length for the user's happy is the average of these 2 blocks, which is 2.5 hours. For all these 3, we plotted the heat map for the emotion self-reports. We observe that for each user, there exists a group of users exhibiting similar self-reports. So out here, if you observe, you'll see that the light-colored values are of similar users, or the dark color are of different users. Similarly, out here, you'll see that there are certain patches where the group of users are similar. They have reported similar self-report transition probabilities, similar persistence effect, and similar emotion strength. We believe that the data amongst these users may be shared to train a model to estimate the missing self-report of a user who may have dropped out of an ESM study. Once we could identify the similar users based on the self-reporting characteristics, we investigate if these self-reporting attributes could be used to distinguish between emotions. For emotion transition probabilities across emotions, we observe a heavy diagonal indicating that once a user is in a particular emotion, they are more likely to report the same emotion in the next self-report. This observation may help in determining the missing self-reports. Next, for persistence time comparisons and sequence length comparison, we performed the Kruskal-Wallis test, which revealed the significant effect of emotion on persistent time and sequence length. Overall, we noted that these self-report characteristics vary significantly across the emotions, and thereby may be used to develop machine learning models for estimating missing emotion self-reports. We next describe the MUSE framework. We use multitask learning to estimate the emotion self-reports because it leverages well on the concept of generalization and it's known to return superior performance if the tasks are related. We consider learning a self-report prediction of every user as a task. So the MTL internally shares knowledge amongst related tasks and estimates the emotion self-report for every user. The inputs to the framework are a combination of emotion self-report characteristics. The shared layer out here that you can see is designed so that it allows learning features of one user using related features from other similar users. This data sharing allows the model to learn a generic representation by leveraging self-reporting characteristics similarly. Finally, the task layer out here allows learning specific representations. In this layer, the traits of individual users are taken into consideration to estimate their emotion self-reports. This layer ignores inputs from any of the other users by assigning them with a very small weight. We use the MUSE framework to evaluate the self-reports and estimate the performance of the homogeneous data set. We split our data into a 60-40 split for every user, where the initial 60% is used to train the model and the remaining 40% is used for testing. We train the MTL model using the initial 60% data combined from each user and test it on the remaining 40% data of one user at a time. Overall, we show that the user-wise emotion user-wise and emotion-wise AUC ROC performance of MUSE framework. We obtain an average user-wise AUC ROC of 84% in this case, while the AUC ROC is more than 60% in 83% of the participants. For emotion-wise AUC ROC, we observe that the relaxed emotion out here is the most accurately identified emotion, with a mean AUC ROC of 82%. Next, we performed a user study with a heterogeneous population using the same experiment apparatus as you can see out here. Specifically, we recruited 30 participants for this study with a diverse profile in terms of geographic location, qualification, and background. They also had varied demographics. These participants used our application for a total of 8 weeks. Overall, they reported 7314 self-reports. We performed various experiments with the heterogeneous dataset. However, we only report the AUC ROC results that we obtained for the dataset. The experiment was done in a similar manner as it was done in the case of the homogeneous dataset. Overall, we obtained a user-wise AUC ROC of 82%, with 63% of the participants achieving more than 80%. In terms of emotion-wise AUC ROC, we again identified relaxed emotion the best, with an average AUC ROC of 85%. Now, the obvious question is, what is a downstream application that can use MUSE? We developed a smartphone keyboard interaction-based emotion detection task. We performed a 2-week study in the wild with 14 participants. We developed an Android keyboard that can track typing interactions. One must note out here that we did not capture any actual text, but rather we characterized how they were typing. That is, how fast they were typing, what was the inter character spacing and all. We again collected the 4 emotions via a pop-up that's similar to what you have already seen previously. We correlated the typing pattern with the emotion self-report and developed an ML model for the emotion inference. To evaluate MUSE on this downstream task, we evaluated 2 scenarios. One where we used the original self-reports for emotion estimation, and one where we used MUSE to generate the self-report. The figures here show the comparison of self-report in the 2 cases. Here we see no significant difference in emotion inferencing when the original labels were used and when MUSE-generated self-report estimates were used. This shows that MUSE can estimate the self-reports accurately. Thus, researchers do not have to discard data of users when they drop out of studies in future, and can use the MUSE framework to estimate these reports. Thus, to conclude, in this presentation, we introduce you with the MUSE framework, which is a multitask learning framework for user similarity-based emotion self-report estimation. We demonstrate how emotion self-reports can be quantified. We evaluated MUSE on 2 large studies and 1 downstream task, and demonstrated that MUSE was useful in estimating missing self-reports, even when users dropped out of the study. These findings demonstrate the probability of reducing the data collection overhead for studies designed by estimating the missing self-reports. With that, I'll conclude this presentation. You can find more details about this work in our paper. We look forward to interacting with you during the conference. Thank you.